by Professor Yuh-Renn, who is also the professor and chairman in Graduate Institute of Photonics and Optoelectronics at National Taiwan University. And Professor Wu received his bachelor degree in physics and also master degrees from the Institute of Communication Engineering at National Taiwan University. He then obtained his PhD degree from the University of Michigan at Ann Arbor in 2006. He is now a professor and Institute of Photonics and also Optoelectronics and also the Department of Electrical Engineering at National Taiwan University. And his research area focuses on the analysis and characterization of optical and semiconductor devices. He developed a multi-dimensional Poisson, a drift diffusion, and Schrödinger equation solver, which is widely used now in LED research societies. And he also developed Monte Carlo techniques in the analysis of carrier transport and also heat dissipation in high power and high frequency gallium nitride HFET devices. Professor Wu focuses on developing simulation technologies, which we will see later, and decided to work on the QKD simulator in 2020. And he was also awarded the Wu Da-Yo Award in 2015 from MOST. And is currently a co-PI in one of the national team of quantum program building key components of QKD protocol and simulation. Let's welcome Professor Wu.
Okay, thanks, Chairman, for introduction. And today my topic is about the development of the QKD simulator based on DPS protocol. And actually, my talk will be more detailed in the QKD protocol instead of more device related. Okay. So before I start my talk, I just give our team member introduction. So in this QKD team, we are from the Graduate Institute of Photonics and Optoelectronics device. So we are more engineer based. So ideally, we want the device from the physics point of view, because most QKD right now in Taiwan is still mainly in physics department. So we want this technique can become real and in industry. So in our topic is just try to integrate all these technique. We are not developing something new, but we want to make it maybe in the future it can be mass production. So in this team that we projected for different professors, and they are working on developing like light source, how to integrate into the system, and the spot detector, and also there's some waveguide decide hope to make a low loss system. Okay, and the Professor Lin is our major member that he will integrate all the system. And in my part, I'm more work on the algorithm of the QKD simulator and try to understand what's real, what will happen when we start to do the quantum communication. Because image that all the signal you got is just single photon. So all the signal you got is just 1 or 0, 1 or 0. So it's like digital, but a lot of noise. So actually, in the first time when I understand the QKD, in my brain, what I'm thinking is, what's the real signal you will get? I think that's very key important. You heard a lot of talk, and you think about the interference and everything. But everything you got is finally just one photon, either in 1 or either in 0. So actually, if you don't expect what kind of answer you will get before you do this, you will simply just crash. I mean, you just say, I got one signal, I don't know what it is. So I think it's very important to have a simulation technique to tell us how the signal will propagate, how it loss, and what kind of signal you'll get. So that's today my topic is that we try to make a QKD simulator. Okay, so this is my outline. And I think the Professor Chu already introduced the quantum key distribution. And we know that QKD has very safe in the quantum communication because it's no clone theory. So I think most people quite understand that right now. So the idea for the QKD is that for Alice, they generate a key. And this key is either integrated by a single photon and phase encoded. And then when you propagate to the bulb, and they can either use the DPS protocol or phase difference, or use the polarization base, and the bulb will measure the key, and then both sides will get some signal, and the bulb will tell the Alice what kind of key you get, and then they get a SIP key. And this SIP key actually there are a lot of errors in the SIP key because you have noise, you have some if maybe they will store your keys, or maybe some noise. So actually the key, even you change the basis and you get the key, actually there are 4% key is wrong, or maybe 5% key is wrong. So when your key is wrong, actually even 1 bit is wrong, your encryption of data is total crash. You cannot share any information. So you cannot tolerate any one key error in the key you get. So you need to make every key to be the same with this large noise ratio. So you need to you need to estimate the QBER. Then you need to use some protocol to do error correction. And then typically error correction they use is the LDPC, linear encoded method, to correct the key. Then finally you can both get the private key. So instead of just understand that the device, how it entangle, how the detector efficiency, actually when you put all the components together, you will find that when you send 1 gigabit signal, and at the end, in the bulb side, it can only detect like a kilohertz signal. So you lose 1 over 1,000 signals. And you don't even know if the only signal you detect is real signal or noise. So that's something you need to be aware of before you start to do the quantum communication, or you do the quantum computing. Also, especially in photonic base, you'll find that they are quite noisy. Okay. So in this project, we are based actually in simulator. We didn't limit our code to be polarization based or the phase shift based. But for the fiber communication, actually it's better for the use the phase shift, because the polarization, or you don't need to maintain the polarization, and you can integrate. So the DPS protocol basically use the phase shift. So you generate a single photon, and this single photon actually is encoded with different phase, also 0, pi, 0, pi. Okay, and when you continue to send this phase information, actually to guarantee you only have 1 photon. So the signal you send, you send 10 signal, you only get 1 photon. So you encoded so many signals, but actually only 1 photon in all these passes. So you get a ratio like 1 to 10. So every 10 signal, you get 1 phase. Okay, so when Alice sent a signal, he encoded 0, pi, 0, 0, and with the MZI interferometers, that, for example, he sent the 3 paths, and actually the bulb will detect the interference of 0, pi, 0 and 0, pi, 0, and you get 1 and 1. Okay, this interference. So ideally, you will get the photon in either the T2 time, or you can get the photon in the I think T4 time, or you can either get photon in different time, T1, T2, T3, T4. Okay, so that's the idea, you get a signal, but actually you have only 1 photon. So in this long path, you have only 1 photon, and actually you don't know which location the photon will be. So although bulb continue to detect but you only get one photon in certain time slot. For example, T2 time slot, or maybe T4 time slot, you got one photon. Then you will tell the Alice, say, okay, I got photon at the T2 time. So Alice will know the T2 time, what kind of phase is sent, okay? Then both sides will know the key. So this is the idea of how the QKD to be secure. Because for Eve, even he know which time he detected, he didn't know the signal is 1 or 0. So in the Eve side, he didn't know what the signal is 1 or 0. So even he tried to eye-dropping, but it's not working, okay. All right. All right, so this is the idea of protocol. You use interference, and if you detect a photon at the T2 time, then you tell the Alice, so you know the signal is, the signal he sent should be, okay, should be 0.0, okay, 0.0. And if you detect in this time, then you will know the key you get, it should be 0.pi, also different kind of key you get. Sorry that this pointer is not quite easy to use, okay? All right, so how to do the simulator? So ideally that, I know if a lot of optical guys know here that, you know, when you try to do optical wave design, you have many simulators, but that's based on the real time, okay? They do the phase propagating, they do the interference. It's just like optical simulation. However, this kind of signal, you just have strength. So you have signal either, when you check the output, you will get the signal either a 1, 2, 3, or maybe 1.2. So you get a continuous probability. But in a single photon, in a quantum communication, you only have single photon. So all the photon, even it has the path shape information, or it still has its wave, but all the probability turn out to be one photon. So when you try to simulate this, you can only say, this series of signal, there's only one photon in this signal. So in a simulation part, oh, okay, we need to distribute the photon to be a single data unit for the simulator. So you put a photon, although you with this phase encoded, then you can try to send the signal to the attenuator, then the signal become weak, and then amplitude becomes small. Then go into fiber, you have some percentage of loss. Then you go into the interferometer, so you have 50%. So everything is done with the Monte Carlo technique. So that we know the probability, okay, we know the probability of going to, up or down by 50. So we use the random number, and you use the Monte Carlo to get the direction of how the photon propagates. Okay. All right, so the different from the optical simulator is that we use the discrete event simulation. So we use single photon as a source, then we just simulate how the photon go out from the source and then to the waveguide, and how much loss, and then go into the fiber, how much loss you get, and then go into the interferometers, whether you go up or down, then you get to the detector, and the detector you will decide which detector you will detect. If it's not reached, you will register, okay. If it's refracted, you go to the loop again, and it continues until the end of photon, you get a signal. So it just fully simulates the transfer process during the whole device. All right, so we try to make all the components. For example, you have a basic device, and you have a photon source, and you have different input module, and you get the signal going to filter like MZI and SPD. Everything is doing the modularization. So you have different device, and you just like the SPICE, or maybe like the FirmLab, something like that. You just connect all the device, and you put source here, and you can, at the end, you can get the signal. All right, and use the Monte Carlo method to decide the propagation. All right, so we know that when you get the shift key, you have the quantum bit error rate to generate, because you have a dark photon, and you also have like attenuation, or maybe something will cause the error of your QBER. So usually, like the reason to get the QBER is like your path is not square, so you have a spatial shape of the path, and your visibility, also your interferometer, of course, now it's not 50-50%, or there's some loss in the interferometer, and you have some dark-on rate, and you have some after passing rate. Okay. All right, so this is a result from our simulator. So we put a path, okay, the repetition period is 1 microsecond, and we put the shape of the path, or that is like a Gaussian path. You have a rise time 5.8 nanosecond, and the fall time is 8 nanosecond. So it's like a stair-size shape of the path. So when you send the path to the whole system, you will get, if you put different path widths, you can find that the QBER, okay, actually the path, this is the definition of path period. If you separate the path to be a larger separation, okay, you put the path period to be larger, you can find that the error you will get, because you have a detection window. So if you separate the path to be a larger distance, then you can reduce the QBER, okay, in the system. And then if you have the detection window, okay, detection window is defined by the open time of the gating of your single photon detector. So if your gating time is large, you can find that you have a larger QBER, because it's possible you get a signal of the T1 time. For example, T1, T2. If you open the window, you have higher chance to get error. And if you have a smaller window, you have a lower key rate. So actually, you need to compete against the opening window, gating window. You have a larger window, your key rate is larger, because if you have a smaller window, it's possible you cannot detect any photon. So it's not amplitude since, it's just 1 or 0. So if you put a very small detection time, you can just get 0 signal. Or you cannot get some signal like 0.1 or 0.2. Or you only have 1 or 0. So that's the problem of the quantum QKD simulation, is that, not simulation, in real condition, is that you need to choose a good gating time to get the signal to be valid, okay? All right, so this is the inference of the time window and the path period, okay? It's the same thing, okay? So after you get a key, for example, you get a key, Bob get the key, and Alice get the key. Then Bob will say, okay, I get so many keys, and what time I detect the key. He will tell the Alice. But actually, there's a QBER. For example, just as I said, there's 4% QBER. So what's the next thing we can do? Is that we need to do the so-called error correction. So in order to get the real key number, so in the Alice part, in the Bob part, you will try to encode it, the key with some matrix. They multiply the matrix. They send an error correction key. And this key is very hard to do the reverse calculation. So this matrix times this key, you get the error check key. Then the Alice will use the same matrix, try to do the operate, or try to operate the signal. Okay, so Bob use the random number series, try to encode the key he got. It's sent back to the classical channel to the Alice. So what Alice get, the encoded key, and plus his original key is his accurate key plus the error. So the original signal will be canceled, and with this signal, Alice will try to iterate it, operate what kind of key it should have, try to make C plus E to be 0. So if you get C plus E to be 0, then you get a correct key. So you get your key to be the same as the Bob, as Bob get, okay. All right, so LDPC is not a new protocol. It's defined by IEEE. There are many different ways of LDPC defined. So we test that different IEEE standard that you can reduce your QBER. For example, if you use IEEE 11AD, then if your QBER is 1%, you cannot get a signal free. But if you use other like 11N, the protocol, you can correct the QBER up to 6%. So if you have 6% error in your system, then you probably need to use the IEEE 11N standard to get the QBER correction. Okay. So this is what we applied. Is that we applied these two technologies. So our initial QBER is like 5%. So after the error correction, you can get the exactly right key. Okay. Okay, you can see that the original error key here is 5%, and the final remaining QBER is 0. Okay, so that's what you get. Originally, this is Alice part, this is Bob card, and actually before correction, that's the shift key Alice get, and this is the shift key Bob get. So you can find out, of course, we play like God. So we know Alice key is 0 and the Bob key is 1. So you know that the key is wrong. You know the key is wrong, and but actually in real condition that Alice and Bob didn't know which key is wrong. So we cannot say, oh, you are wrong. So we just exchange. No way to exchange. So Bob will need to send need to use LDPC protocol to encode the key he got, and he will send back to the Alice, make her to change. So after operation several times, the Alice final will get a key to be correct, to be 1. So you can see the right column is after the correction. Okay, after the correction, you will get the key of two sides is the same. Okay, it's the same. Okay, this is a video and show the technique we developed. Okay. Sorry, this is in Chinese caption, but I guess most of you can read it. Okay, maybe a few people cannot read it. So it's like a graphical interface, like a user can decide the laser, phase modulator, and they can put all the components to connect. Okay. And then after connect, you can find this. Oh, sorry, I just should not press enter. Sorry. Okay, I think I cannot press anything. This is just the video. Okay, so you put all the components. Sorry to delay 1 more minute. Okay, so you connect all the components and decide how the signal sending direction, and it's just like some simulator that we quite usually in the experimental part, and we can define the phase modulation and define all the modules parameters. Okay, and you can set up the define what's the attenuation. If you have fiber, what's the distance of the fiber, what's the loss rate, and put everything to be a simulator and try to run many photons in the systems. Okay. So this is the input file to the simulator. Okay. So be aware is that when you get all the keys from both sides, okay, you can find that actually this is initially how Bob get. You can find that Bob almost gets 0 keys. The left-hand side is the key sent by Alice, and this right-hand side is the key measured by Bob. You can find only a few % of key was detected. Other key are all lost, or most key are lost. Okay, so when we try to remove all the lost key, then finally we will get the safety. This is getting the safe key. And that's what you really detect. You can find out every 50 photons, every 50 period, you lost 1 photon. Okay? Then after the key correction in the red color one, okay, then you can correct the signal of the QKD. Okay. So from simulator, we can expect that before we do this experiment, we can find the signal will be very noisy, and a lot of qubit you expect to detect the signal, they were all lost. They were all lost. Okay. So let me quick show this. This is the inference of the parameters. That if your path is not perfect, and then you can get even you expect you get 0, you get 1 here, but you can find the probability of getting 1 here and here is not symmetric. So you get higher QBER. You get higher QBER. And this is the signal you detect. And if your device is a polarizable detector or non-polarizable detector, okay, like this polarized detector and non-polarized, you can get more noise. Okay, you can get more noise. And finally, is that if you have attenuation in the fiber, you can find that even you put a very high clock rate, your key rate is very low. But if you have going to 50 kilometer and 150 kilometer, you have very high clock rate, but your key rate you got is only like a kilohertz. So you got a lot of loss. Okay. So this is my final talk. Thank you. Okay.
Thank you very much. So maybe we can have some questions from the audience in this room. No? Then I have a quick one. So,
okay.
Well, it's very interesting to see your simulation results, but is there any experimental result you can compare with, like experiments from Professor Chu's?
We don't have experiment from him directly, but we compare to the papers. This is the black color is the paper's device system. They try to encode the phase. It's like 0, phase. They expect to get a detector 2 to get all the phase. Mm-hmm. So they measure the probability. The black color is what they get. And because there is some problem of their device, so when they try to encode pi 0, phase, they found the probability of this one and this one is different. Okay, detector. Ideally, it should be symmetric. Mm-hmm. So we try to put our simulator, and we find that if your Gaussian shape path, if you have a symmetric in the rise and the falls time, and you have a little bit phase delay, you will cause this asymmetric. Okay, we can exactly reproduce their result for probability. So I think the simulator itself can explain many experimental observation from the point of view. Okay.
Good to know. Thank you very much. So do you have any? Yes, there, please.
In your simulator, is there a difference between a genuine single photon state versus a weak pulse laser at a few photon level?
We only simulate single photon level, so like we try to assume it's like a attenuator. We didn't simulate entangled photon. Is that what you want?
So what you simulate is a weak pulse.
Yeah,
right?
weak pulse.
Yeah, but if you input a genuine single photon state, so like those generated by SPDC, mm-hmm. Would the simulation result change?
I'm not quite sure, but I can expect there's some difference. I can expect some, because we haven't done that yet. But actually there's a result here. Maybe I missed is that okay. I don't know if I have that. Okay, I didn't say is that Okay, the MPN, the attenuation, if you have different attenuation coefficient like 1 to 10 or 3 to 10, then actually you have different key rate you will get. Okay, you can detect from the simulator. So it's very important that you need to keep the space of the photon to photon, like maybe 0.2 would be the best. Okay, to keep the spacing of each photon. So you need to attenuate to every 5 pass you get 1 photon. You cannot make 1 pass 1 photon, although you think the possibility to get is most higher. But actually you have a lot of interference in the simulation. So you'll find that the best one is not just attenuate to 1 photon per pass. It's better 10 pass per photon, or maybe 5 pass per photon. It could be the best condition. Okay.
Okay, thank you. If any other quick questions? If no, then I think it's about time for us to conclude this forum and this section. So before that, let's thank Professor Wu and all the speakers in the afternoon session.